To simplify radical expressions, we're going to need a couple of facts. So here we have the nth root of x to the n. It seemed like in the last lesson, the answer to this would just be equal to x. So that is, if you were to like square something and then take the square root, it's like you're doing nothing at all. But let's examine that in example 1. So let's see, here we have the square root of 7 squared. That's the square root of 49, and the square root of 49 is 7. So it kind of seems like this is okay. If you take the square root of something being squared, you're just left with that value. And this should hold for a cube root as well, or a fourth or fifth root. But let's see. The cube root of 4 cubed, that's the cube root of 64. And that value simplifies back to 4. So again, it just seems like it canceled the cube and the cube root to give me 4. But what about in this one here, where I'm taking the square root of -7 as opposed to positive 7? Well, in this case, okay, the square root of -7 squared becomes a positive 49, but when you take the square root of 49, it gives you positive 7. And this is something to look out for, where if you're dealing with an even root, like a square root, and you have a negative here, you actually get the positive answer over here as opposed to the negative one. That's why I have these two different facts listed up here, where sometimes the nth root of x to the n is simply just x. This happens whenever n is an odd number. But if you have an even number, like a square root, the answer isn't just x, it's actually the absolute value of x. Notice here, we started with -7, but the answer was the absolute value of that, which is positive 7. And this happens whenever n is even. What we'll do for the remainder of the lesson is assume that x is going to be a positive number or 0, which means when we get to the very end, we won't have to worry about this absolute value. But in general, if you are taking the nth root of x to the n, where n is even, we would have to place this here. The other rule that I wanted to focus on is if you're taking the nth root of a product, what you can do is break the product up into two different nth roots. Let's see how this can help us simplify the couple of expressions in example 2. So starting with the square root of 40. What I'd like to do is look for perfect squares that multiply to 40. So maybe just like examining this number a little bit. 40 is equal to, well, it could be equal to 2 times 20, but the square root of 2 and the square root of 20 don't simplify nicely, so we kind of proceed to look for something that works a little bit better. Well, 40 is also 4 times 10, and the square root of 4 actually is 2. It works out perfectly. So the goal here is to take 40, replace it with this, and then break the square root up into a product. So here's what we have. The square root of 40 is really the square root of 4 times 10, but this is the square root of 4 times the square root of 10. And as we already noted, the square root of 4 is 2, and then we have the square root of 10 left over. This process will end the second that there are no more perfect squares within the number under this root symbol. So here I have the square root of 10. Does 10 contain a perfect square? So we could examine that. Well, let's see, 10, that could be 1 times 10, but that's no good, or perhaps it would be 2 times 5. Neither of those are perfect squares, so this actually is our final answer. The fact that there are no perfect squares within 10 means I can't simplify this anymore. Let's see how this idea can help us simplify this expression here, where I'd like to add these two and then subtract the last expression here. So this is 10 square root of 3 plus the square root of 27 minus 3 the square root of 12. It doesn't look like we have any like terms, so we can't really add or subtract. But if we could somehow make each of the square roots the same, then we could add or subtract how many of those things that we had. Starting with the square root of 3, 3 can't be broken apart at all, so I have to leave this one alone. Let's examine the square root of 27, so let's look at that separately. Does 27 contain any perfect squares? So 27 is equal to 9 times 3. All right, so this is going to work out really well, where if I take the square root of 27, it's really the square root of 9, which is perfect, and then the square root of 3 is left over. I wonder if that'll also work for 12. Let's think about that one too. All right, for the square root of 12, again, I'm looking for perfect squares within 12. Well, 12 is equal to 4 times 3, and the square root of 4 is 2. I'm going to replace 27 with 9 times 3, and 12 with 4 times 3. Let's see what we get. So this is 10, the square root of 3, plus, okay, that's the square root of 9 times 3, minus 3 times the square root of 4 times 3. I'll leave the first term alone, and note that I can break these products into two separate square roots. Same thing goes for the square root of 4 times 3. That's the square root of 4 times the square root of 3. I've done this in a way where the square root of 9 is 3, and the square root of 4 is 2. So let's see, we get 10 root 3 plus 3 times root 3 minus, all right, here I have 3 times the square root of 4. That's really 3 times 2, which is 6. So I have minus 6 square roots of 3. Because every single term has a square root of 3 attached to it, it means I can simply just take 10, add 3, and then subtract 6. I can pretty much treat the square root of 3 as it were a variable. So we have 10 plus 3 is 13, minus 6 is 7. So 7, the square root of 3, is the final answer for this problem. So when examining expressions that contain square roots or cube roots, you can still simplify these expressions if you can break apart the numbers into perfect squares in this example. And for the last example, I want to use these previous ideas to simplify these three expressions. The difference is these now contain some variables in them. So let's start with this here, 16x squared y to the fourth. As we saw in the previous lesson, if I can write each of those as a perfect square, simplifying this is going to be very easy. And there's actually no problems. This is the square root of, well, 16 is 4 squared, and x squared and y to the fourth have exponents that are both divisible by 2. The reason this simplifies really well is that this means 4 squared times x squared times y to the fourth, all to the 1/2 power. We can simply divide every single exponent by 2, which gives us 4x and y squared. Because I've assumed all the variables are positive, I don't have to worry about any absolute values, and this would be my final answer. So it's pretty simple because, again, each exponent was divisible by 2. Let's check this out in the next example where, okay, I now have the square root of, all right, 81 is 9 squared. Okay, that's great. X to the fourth is also perfect because 4 is divisible by 2, but now I have y to the seventh. And that's a problem. I can't simplify this under the square root because 7 is not divisible by 2. So what can we do to get around this issue? So here's a trick that we can use. I want to write y to the seventh, so I end up with an even exponent. And the closest one I can use is to the sixth. I'm now going to break this up into the product of y to the sixth times y to the first. The trick here is, instead of using y to the seventh, I'm going to replace it with y to the sixth times y to the first. Clearly, if I add those two exponents, it takes me back to 7, but this 6 is now divisible by 2. I'm going to put this expression right here. So now if I proceed by taking square roots, I'm taking the square root of 9 squared, so that's just going to give me 9. I then take the square root of x to the fourth, that gives me x squared. Again, I'm just dividing the exponent by 2. And now here I have y to the sixth. If I take the square root of that, I divide the exponent by 2, which gives me y cubed. And then the only thing that I can't do is deal with this y to the first that's left at the very end. It actually stays underneath the square root because I can't take that piece any further. So what we have here is, by breaking this apart into even exponents, those all come out of the square root, but then this y to the first we couldn't do anything with, so it is left over underneath the root symbol. And this is the final answer for this problem. So let's try this idea with a cube root. Again, what we're looking for here are exponents that are divisible by 3. And 10 and 22 are definitely not. But let's try anyway. So this is the cube root of, now I know negative 27 is negative 3 cubed. That's perfect because that exponent is divisible by 3. But now we come to x to the 10th, which is no good. However, you can break this apart into x to the 9th times x to the 1st. This is a good choice because, well, 9 you can divide by 3. There'll just happen to be this 1 that's left over at the end. I'm going to replace this with this, and I'll write it here. That's x to the 9th times x to the 1st. I want to do something similar with y to the 22nd power. I need an exponent that is divisible by 3. And the closest one that I can think of is y to the 21st power. 3 definitely goes into 21. But you have to have y to the 1st left over, so it adds back up to 22. What I'm going to do is replace y to the 22nd with this expression here. Okay, here's what we have left over. If I take the cube root of negative 3 cubed, I have negative 3. If I take the cube root of x to the 9th, 9 divided by 3 is x cubed. I cannot do anything with this x. It'll just be left over at the end. The next piece I'm coming to is this y to the 21st. If I divide 21 by 3, I get 7. And then I end with this y to the 1st, but I can't do anything with that either. What this means is at the very end, I have a cube root of x to the 1st and y to the 1st left over. These can't be simplified any further, and this is my final answer.